Industrial maintenance is commonly viewed as a strictly mechanical function, a world of turning wrenches, swapping parts, and physical labor. In high-performing organizations, physical repair is the execution arm of a deeper and visible information processing system. Level 1 ad hoc facilities have disconnected nodes, flashing alarms, and isolated databases. Level 5 world-class operations have data moving in a continuous loop between equipment and a central hub. Organizations in this reactive state maintain massive budgets while suffering chronic, unplanned downtime. This occurs when management treats data entry as an annoying byproduct of physical work, rather than the primary fuel that drives maintenance strategy. Transitioning to a proactive strategy requires a continuous loop, the Plan, Do, Check, Act, or PDCA framework. The PDCA framework functions as a mechanical data circuit, where information must flow sequentially to be effective. If data degrades at any single node, through a missing failure code or an ignored asset history, the circuit breaks. Without a complete flow of information, the organization lacks the evidence required to validate or improve its maintenance routines. Moving from reactive firefighting to predictive asset management depends entirely on mastering the flow of data through these 4 quadrants. The cycle begins on the floor, where operators identify early signs of abnormal conditions, a strange vibration, a temperature spike, or a drop in performance. These observations feed the plan phase. Planners convert this raw data into specific job scopes, identifying the tools, parts, and skills required for the repair. To move away from reactive repairs, the planning process must account for asset degradation over time. This is the PF interval. The curve tracks equipment health over time. Point P marks the potential failure, the first moment we can detect a defect. Point F is the functional failure, where the asset can no longer perform its job. By plotting condition monitoring data along this curve, maintenance teams can schedule a condition-based intervention shortly after point P. This intercepts the failure before it reaches point F. This data-driven approach targets work based on actual equipment health, replacing traditional schedules that rely on arbitrary calendar intervals. If the data entering this phase is inaccurate, planning becomes a guessing game. This leads to scheduling bottlenecks and part shortages that stall the maintenance process. High-quality planning data serves as the foundation for a stable, predictable maintenance schedule. Once the work is planned and scheduled, it moves to the physical asset for execution. This is the do phase. During execution, technicians perform 2 critical tasks. They restore the equipment to a safe state, and they capture the ground truth of the failure. All observations from the field must be recorded in the Computerized Maintenance Management System, or CMMS. Technicians are the primary data generators in this cycle. The information they provide determines the success of all future reliability analysis. The system operates on a garbage in, garbage out rule. Vague notes like fixed pump provide no value for future planning. High-integrity data requires using standardized codes to describe exact failure modes. Technicians must record exact labor hours, materials used, failure codes, and detailed observations of the equipment's condition when they arrived. Supervisors act as the quality control gatekeepers, ensuring work orders are only closed when the data is verified and complete.
The accuracy of the information recorded during repair determines the quality of every maintenance decision made in the future. Once the work is documented, the organization must analyze that information to determine if its maintenance strategy is effective. In the check phase, execution data is aggregated into trend lines. This provides the evidence needed to verify if the current maintenance plan is actually preventing failures. Key performance indicators like mean time between failures and mean time to repair are used here to measure reliability and repair efficiency. We also analyze schedule compliance to see how well the workforce follows the plan without being distracted by reactive work. For example, an oil and gas facility analyzed its work order history and found that 50% of its preventative maintenance tasks resulted in no actionable findings. This over-maintenance was caused by following generic OEM intervals that didn't match the facility's specific operating conditions, leading to thousands of wasted labor hours. Without high-quality closeout data from the previous phase, these inefficiencies remain hidden, causing the same mistakes to be repeated. The check phase turns raw data into knowledge, showing management exactly where the maintenance plan is succeeding or failing. The final stage of the system is turning analytical insight into structural change. If this step is skipped, the information flow becomes a dead-end line where data is collected but never utilized to drive improvement. In the act phase, we close the loop. Insights from the check phase are fed back into the plan phase to refine the next maintenance cycle. This results in tangible improvements, such as updating risk assessments, revising job instructions, and optimizing spare parts inventory. Teams use root cause analysis to modify preventative maintenance frequencies, moving away from generic guidelines towards site-specific realities. Organizations that rigorously apply this closed-loop process see a steady increase in equipment reliability and maintenance maturity over time. The ACT phase ensures that maintenance strategies evolve, converting costly field lessons into permanent operational upgrades. A theoretical PDCA loop still fails if departments hoard their information in isolation. When production, engineering, and maintenance keep independent datasets, they create data silos. To achieve cross-functional visibility, these datasets must merge into a unified enterprise asset management ecosystem. Achieving world-class maturity requires an integrated platform and cross-functional planning to ensure everyone is working from the same data. Many organizations believe that simply collecting a massive volume of sensor data makes them data-driven. Data volume is not the same as data usefulness. Excessive data from wrong frequency maintenance produces noise rather than value. Only validated and analyzed data can support better decisions. Maintenance teams must also look beyond generic OEM manuals, which rarely account for the specific stress and operating context of a unique plant floor. Ultimately, the CMMS is only as good as the information people enter. If technicians and planners lack discipline, data quality decays and the entire system fails. Integrating actionable data into daily routines shifts a maintenance culture from reactive firefighting to optimized predictive performance. Maintenance performance is a direct reflection of information quality. Success requires embedding data as the core decision engine across every step of the maintenance process.